Hello, I'm Markus. I also like to do a lot of open source work. So my GitHub handle is pacman82. Most of my open source work happens in Rust, and I think my most meaningful contribution is probably the odbc API binding. So odbc is for accessing databases in standard, and I maintain the bindings for Rust for it. So data engineers might also know my odbc to Parquet tools, and there's a few other crates, but I won't go in there. Personally, I've done most of my career as a C++ developer, but I'm using Rust since 8 years, roughly before it became stable in version 1.0. And currently, I'm the head of engineering at Aleph Alpha. So what do I want to talk to you about today? For once, I want to talk to you for what we use Rust at Aleph Alpha. And then I want to drill deeper into two specific problems, which also spawned the creation of two open source crates. And I want to share the problem with you so that you might know how to pick them up or improve upon the solution. Okay, for that, I need to provide you with a moderate amount of context and a little bit of advertising. What we are doing at Aleph Alpha, we are striving to create sovereign European AI. We are targeting enterprise customers mostly, but any private person can go to that link, use our playground and use our product or use our API. So one question I want to elaborate on from the previous speaker was where to get the embeddings for the models for the search engine. Well, OpenAPI is one step, but you can also get them from Aleph Alpha. So just to elaborate on that. However, what I've prepared here is a different kind of task, not an embedding task, but a completion task. Which, what you see here is a slightly younger version, both of our UI and myself. And this is a completion task based on the multi-model prompt. Multi-model, because there are two modes of input here. One is text and one is a picture. And the model is trained on text. And what it will do, it will complete the text. So it will just continue writing the text. And the text is phrased as question, Q, and then there's an A for answer. So the model is primed, okay, now probably there should come an answer to the question. And before the question, there's a picture. And so that results in the completion, a man with glasses and a beard, which is a reasonably accurate description. And this I will use to explain what we do at Aleph Alpha. So how does Factor Rust into it? So at Aleph Alpha, we are a fairly young company. So there has never been, at least from my point of view, an Aleph Alpha without Rust. I was hired via the Rust newsletter. That's how I discovered the company. And so I cannot tell you a tale, oh, this is all the production errors we had, and when we switched to Rust and all went fine. In that regard, it was always fine. What I can tell you, though, is what we are using Rust for and what we are not using it for. So what we are not using for is the core domain of AI and natural language processing itself. So Python just looms large here with PyTorch and all these fancy bindings, and it's just very much loved by our researchers, and we wouldn't take it away from them. Also, the prototypes, quick POCs, are usually also done with fast API and Python. What we do in Rust, though, is inference preprocessing. So inference is the process of actually using these models in production. And what the user sends is not quite what goes into the model. So all this text has to be converted to numbers in various ways. Rust is very well suited for this job. Also, data pipelines, these models are trained on large amounts, terabytes actually, of data. And there's a lot of pre-processing and command line tools and stuff that goes into which does it, and it's reasonably fast doing it in Rust. And yeah, basically, if it's done by the engineering team at Aleph Alpha and there's no good reason to use another language, it's usually done in Rust. And all the boring stuff we do in Rust. And the nice thing about it, so that's not as negative to me as it may sound, it stays boring. Like doing a lot of DevOps and operations, right? Boring becomes a pretty positive term. And in short, I could summarize it that we use Python for fast idea iteration and we use Rust for production. So somebody wants iterating over ideas fast. He doesn't want to be bothered by, oh, what would happen if that would go wrong. He just wants to move on to his next plot, to his next idea. And in Rust for production code, I actually want to be bothered with everything that could go wrong. And this design is actually not quite right. Please think about the ownership model again. So that's roughly how I decide what to use. We, of course, use TypeScript for everything UI. No argument here. Another thing that I found interesting was hiring Rust developers. It turned out that I thought this would be hard, and in a sense, I was right. But the last 3 developers which were hired, they didn't use Rust before at all, but still in their second day after their companies, commits from them were already running in production. Pair programming, of course, helps a lot with this. But I reasonably cannot see anymore that Rust is hard to learn. People can pick it up really, really quickly. What is actually hard to learn is maybe ownership model or software design, but these were concepts that existed before, right? And a C++ programmer who understood ownership, he can just pick up Rust really quick. And yeah, so for me, I would say hiring Rust developer is hard, but Rust doesn't factor into it because I don't hire Rust developer. We just hire good software engineers, and that was always been hard. But previous knowledge of Rust itself is not required. They pick it up all fairly quickly. Okay, moving on to the open source grades, which have been spawned by little problems we had at Aleph Alpha. But one honorary mention must go to the Aleph Alpha Rust client, right? So the majority of our features is actually covered in the Python client. The Rust client is more like a spare time, rainy day project of myself. Everybody's invited to contribute. It doesn't cover the entire API by far, only whatever I need in that moment I add it. But embeddings are in there, and here is a code sample for completion task. Basically what you've seen in VI before, just with a cat picture instead of a picture of me. And the first problem I want to talk to you about is waiting on external events. So for this, I want to share with you a little bit of an architecture slide, a block diagram. So we have here a user want to send his completion or embedding task. He can use various means of it for this. But ultimately, a request reaches our API. And now the API does distribute these tasks to a worker. However, it does not send a request to a worker and get an answer. Instead, the worker fetch these tasks batch-wise and answer them batch-wise. So what does this mean for a control flow? A worker might ask for work. This is just one example of how it could happen. And when a user sends a completion task, the API does a bit of work and answers the worker's request for work, because now finally there's work in the queue. And then the worker answers with the completion. And now we want to send the completion to the user. Okay. Why is this a problem? Well, what could be a bit of a problem? Let's consider a code sample. And in this code sample, I switched to architecture a bit. Now I just have a worker, which is a service. I send him a completion task, and I await the response. And now I can simply wait for whatever result I want to have in the handler of my service, and all is good. So, but that's not actually what we do, right? Instead, I have a user calling a completion route, and at one point in time, a worker will kindly give me a result to the task. And now I have to do something here so I can wake up here. And the question is, what do I wait here? What is the future I'm awaiting? And it turned out to me that I already solved these problems some time ago. This is the README of a throttle semaphore server. A semaphore is a synchronization primitive, like a generalized version of a mutex. And this is throttle is a semaphore service for a distributed system, not itself a distributed system. This is important distinctions, but usually that's what you want. People always ask for distributed mutexes, but they want actually a mutex for a distributed system. And actually, it has a deadlock detention by enforcing lock hierarchies. One of the touching points to the talk earlier. And if we look what throttle does actually, well, it has to have at least 2 clients, so it's fun. So we can wait on each other. And then let's say, okay, client B starts, asks for a mutex and acquires a lock, and then keeps busy with the lock. Meanwhile, client A asks, but throttle will answer him right away, okay, you don't get it, or delay that answer. And after a while, client B releases the lock, and then it gives the acquired lock to client A. And this second part of the flow diagram, the part how we answer and what we would wait for in the handler, that's exactly the same. And so I extracted that part out of throttle into its own async-events crate. So the name, actually, I don't like it, which is probably a hint I don't fully understand what I did here. But at least it served me well on 2 occasions. So I thought I might just share it with everybody so it could be useful. And remarkably, once I extracted it, I discovered, okay, it depends on nothing, right? I don't depend on TOC.io or standard async or anything. It's completely independent of the environment, which just, I think, goes to show how smart actually the Rust async await system is designed, and how well the execution is separated from the usage. I was really remarkably euphoric about that, although I only use TOC.io. So and how does it help us with our problem? Well, I could introduce a little struct, neatly also taking some of the domain logic out of the handlers, not following the smart UI anti-pattern, and just an ID. So every task gets its own ID, and we can identify what answer belongs to what task. And when I introduce async events, you can see here the structure is generic. So I could basically do any kind of result, including Rust results to transmit errors, and also the ID type I want to use to identify the event. And then I give it 2 methods. So on the completion route, which is basically the sending work route, I get, of course, the prompt, which is the input. I generate an ID. When I need to send the work to the worker, I will omit how we do that. All the queue stuff is now not interesting for this. And then I just wait off the output of that event. And when I need another route, which tells us the result, it tells us which ID it's for, and the result itself. And here, one of the observers waiting for it will be woken. And that allows me to go back to my handlers and wait simply on the result of the completion. And when a worker reports a result, simply tell it about it. The second artifact, which is also is called log hierarchy. So personally, I'm a big fan of the actor model. And usually the fix for me is actually to switching to the actor model because all the state got too confusing. But sometimes you just say, okay, we don't have time for that refactoring, or sometimes actually not choosing the actor model is the right choice. And then you have the aforementioned deadlocks. And also we had them. And indeed, Rust does not protect them from them. It only protects from not even all race conditions, just data races, but that's actually quite a lot already. But what I decided to do was not to search for actually detecting deadlocks at runtime, just catch it one level earlier, detect any violation of the log hierarchy. The fun thing there is it becomes quite deterministic. And I have even a little demo prepared for that. So in that case, no realistic demo, just one of these academic examples, probably the most academic examples of them all, because it's about philosophers sitting around a table. Each of them has a fork to its left and its right, and they need both forks to eat. And once they have eaten a bit, they lay down the forks and go back to thinking, and then they start eating again. And the interesting thing here is, of course, it's a shared resource because basically each fork can be acquired by two philosophers. So now I will do maybe switch over to my Visual Studio Code in the screen sharing. Let's see if I stop the screen sharing. Present. Share screen. Share screen. Select window. I hope my, it seems like my editor can be seen. Let's create a new shell and let's go to the philosopher's example. I think it's from some older version of the Rust book. I modified it slightly so the philosophers will start the eating thing over and over again. I just run it. And we see here some output. There are 5 philosophers sitting around a table. They all eat. And at one point, it just stops. And that's due to a deadlock. And what I do want to do first, I don't want to fix the deadlock. I just want to find the deadlock way earlier. And for doing that, I just use log hierarchy here and replace the standard mutex with it. And that basically makes every mutex on the level of 0, which means no 2 mutexes can be acquired at once. That means it will fail right away, pointing to me to a line in its error message where the mutex is acquired. So now I get a deterministic error, and I don't even have to wait it for running a long while to see that there's something wrong with my product. What I now can do is I can give each mutex a level. And acquire it in order. That should still crash, just assigning them levels will do nothing. But now, if I acquire them in order, that should fit the bill. It should. That's why you practice your demos earlier. may have, I think I may have switched around how these work. Yeah. Okay. Now back to the slides. I just want to thank you all for listening. There's still some positions for Rust developers open on my team. So if you want to check it out, here's the link. And I thank you all for your attention.